In this video, I want to kind of talk about sort of circuit aspects of talking about what we often call p-n junction diodes. They're just often called diodes. They are an interesting structure because they're often considered like the first nonlinear element people look at. They're two-terminal devices. Two-terminal devices, no state sort of being held usually explicitly in them. There can be capacitance in some small cases, but primarily considered a device where you have a simple current voltage relationship. But they're fairly nonlinear, and they're extremely useful. And historically, there's a lot of interesting aspects. And there's a lot of neat physics. But what does it feel like when I look at them from a circuit perspective? Well, here's my typical device, and I'm going to have voltage across it here. There's a current that'll go down through that device. That current voltage relationship, again, any two-terminal device will kind of have some relationship. That relationship, if I plot it out, looks like this response here, where I have a forward bias region and a reverse bias region. A reverse bias region where it looks like there's almost no current. It isn't quite zero, but it's quite small. And then a forward bias region where it looks like it's pretty flat and then all of a sudden just takes off. And then almost looks like, there's just a huge amount of current. And you get this interesting relationship. Now, if you look at closer into the physics, you actually get a relationship where it's I is equal to IS, which is a parameter for that particular device. That's like the primary parameter for a p-n junction diode. And then e to the v over ut. Ut is kT over Q, roughly 25 millivolts at room temperature, minus 1. So when V is negative, you get this very small term, which is right around minus IS. Typical number, like in this structure, might be, is less than a picoamp. Usually pretty small for a lot of structures, but it kind of depends on what's been built and what you're using. In forward bias, you get this very strong exponential, and if you notice as V gets a little bit bigger than UT, the exponential is going to be the biggest thing there. And so that's why you get this exponential kind of response when it's all done. And so you look at the structure, and there's all sorts of ways to interpret this. One is to say, okay, look, if I get up to a certain threshold, then I have pretty much it all turns on. If I get up to a certain threshold, maybe it's linear-ish. Okay, I can think about different approaches there. And it's important to kind of have a whole perspective of it. The classical kind of circuit, though, that you run into with this, and you see this all the time, is what happens if I have an input voltage with a resistor and a diode here. And what does that output voltage look like as a function of input voltage? Seems like a very reasonable question. And by the way, this is a very classic circuit. One of the things that you might use a diode for is for actually getting light. So if you've ever seen a light emitting diode or an LED, that would be a diode made of various materials that give you various light properties coming out, or maybe optical filters to help that as well. And so you're going to see structures like this, and you might imagine, well, what happens if I take this input and I sweep it and I look at the output voltage? Well, some interesting things happen. When I get for a very, very low, when the output voltage is fairly low, or when the input voltage is low, the output voltage will be fairly low, and I won't get a lot of current through this diode. And so the input and the output voltage are almost identical. In fact, it's almost a straight line. And then once I get a little bit further, I start to find that this diode now has a resistance that's similar. In fact, I get a spot where the diode has roughly an equivalent resistance, and you might say a small signal resistance, to what I have for this resistance here. What do I mean by an equivalent resistance? This sounds like a weird concept. Until you think to yourself, well, I've got this particular current, and I could imagine in the forward bias regime, so the -1 doesn't matter too much, and I could say, well, what would that resistance look like? Well, I could say, let me take a partial derivative of that current with respect to voltage, and and then invert it to get resistance. And it turns out the value I get is UT over whatever that current was. It's kind of a neat result, actually. In fact, you can actually look at this if I take this particular curve and I zoom in into this regime a bit here. What you'll see is here is the current and here is the voltage. And what I'll see is right around this point, I get a particular slope. This is actually right about when it's 260 microamps, roughly. The resistance I get is about 100 ohms, which is actually pretty low resistance given the current that I'm working with, which is kind of a useful technique to notice. And I could even say right around this point that it looks like I have almost this sort of linearized structure of a voltage source and a resistance. Now these two should have been in series. Small misdrawing on my part. But these two should have been in series. And that would give you kind of the linearized model of what you're seeing. In that particular case, then you'd say, okay, I could then say, well, what does that mean here? Well, the first thing is I could sort of look at this equation that solves the space and say, what is the voltage of the current in the resistor and the current of the diode, and equate those. It gives me something of, I can relate Vn equals V out times an exponential of V out. This equation does get nonlinear and a little bit messy. But if you took like sort of characteristic values of R and Is is 100 femtoamps, you're going to get this curve here, this typical measured curve that you would see. And you might get different cases, and you can actually, by taking this curve, you can actually get a sense of some of those parameters. Because this crossover point here is right about when you kind of have the resistance here and sort of this sort of linearized resistance of the diode are about equal. And that crossover point is quite useful. In this case, it's at 0.44 volts. That's when I would get 10K from the diode and 10K from the resistance. And that's something that you can actually work in and solve for and kind of look at the structure. But it's really quite an interesting dynamic and property all the way through this system. And so when you start looking at sort of core circuits for diodes, these are the kind of core properties you see, and without really kind of hand waving. But it's because of these properties you can then make the approximation of, oh, there's a region where the diode is basically running everything. There's a region where the diode's not. This kind of relates to this very strong current and basically everything being off in that space.